the function is not well behaved. Okay. No, you want to evaluate this integral. And well, let's put it in a more convenient form. Usually, because this is a linear function in the denominator, so you want to find the location of where the singularity is, and singularity is on the complex plane because of this gamma. It is an imaginary part, so it's not hitting the real line. If you hit the real line, then there will be a singularity along the integral. Then the integral is not well defined. So that looks good. So you can multiply or take out the minus h bar out, right? Then if the minus sign, it cancels h bar. You can put I in the numerator. That will be changed to omega, and the imaginary part becomes a get out h bar divided by h bar and change the negative sign. Right, and this is minus easy. Right, so the complex integral over the omega plane. The pole is at is at 0 over h bar, and it depends on the gamma already set is positive, so this is negative imaginary on the negative complex plane. So this is minus. Okay, so there's a pole. You integrate along the real imaginary axis. Now you want to figure out, obviously, because of this exponential factor, you want to use the Jordan-Lambda, right? And it's bad enough because the Jordan-Lambda required that the function decrease at least 1 over omega, 1 over z. In that case, it satisfies that. But then now you need to close it one way or the other, and that depends on the sign of t, whether t is positive or negative. If t is positive, and omega has the imaginary part I omega I, right? And I times I is minus. So you want omega, you want the imaginary part to be negative. But t is positive, so the imaginary part has to be negative, right? You know what I'm saying? I need to write it down. So you have this, the phase factor is minus I omega. That's right. So minus I omega t equals to you have the minus I omega real plus I omega I t, right, equals to omega I minus I omega O times t, right? And this is the argument of the exponential function. You want it to be negative, omega I times t to be negative. on the path that on the big circle that you want to close the contour. So for t is positive, you want to close on the contour that omega I is negative. This is t positive. Then the reverse is true if t is negative. You want to close the zero. Okay. Then you apply just the residue theorem. So for the first case, then that loop contains a singularity, a pole, simple pole here, right? And then so the loop is equals to just the integration along the mu part because the big circle is zero, right? Along the big circle, the integration is zero. So you pick up just the residue 2 pi I times the residue, but this is in a negative sense, it becomes minus 2 pi I times the residue at this pole, at this pole. Okay, so the two cases. Oh yeah, no, I forgot. There's not quite any else. I just copy wrong. All right, all right, that's more like it. Okay, and now the positive t case, you get the pi 2 pi and multiply by minus 2 pi I, and the residue is just multiplied by the same factor and with omega evaluated at the pole. So it's e to the minus I, and the location is minus at ECO. Minus as for t is positive. And for negative t, it doesn't have a pole over here. So it would be zero because there's no, the whole thing is energy over the upper brain. So that you cancel I and negative I cancel 2 pi's, everything is 1. It's just 1. So this would be that's the exponential. See if that is the what is actually. It's just write out the real exponential function out. Minus I is minus 1 gamma over 2 h bar t, yeah. And then minus I e 0 t over h1. Okay. Okay. So the only trick is that where you close the contour, you just use the condition for the Jordan lemma to determine that. Okay.